All right, 102 students, let me try another solution. Let's go back a little bit to chapter 4. It's number 6. And this is a conceptual one about the direction. And that was a big part of this chapter. And a big part of our physics is making sure we think in terms of not just numbers and units, but also direction. And so, things like moving at a speed of 3. Let me stop right there. 3 is different than 4. And so hopefully you kind of got the idea of what a 3 would be versus a 4. And then 3 meters per second versus 3 miles per second. See, the units would matter. 3 miles per second is really fast. 3 meters per second is kind of slow. And so the units are important. But also direction is really, really important. And so is it 3 meters per second north or south? Because, that's important. If you're going north and you push something north, it goes faster. But if you're going north and you push it south, it slows down. And so knowing what direction you're moving and what direction you're pushing on it is absolutely important. And so these vectors, and that's why we did a lab on them, are crucial. Anyways, so this one is connected, obviously, to the circular motion here. So I'll draw a little circle. And so it says, okay, so we're going in a circle. So the child rides on a carousel. In what direction is each of the following vectors point? All right, so as you're going around, why don't I just pick a point? It's a carousel, so we kind of have to imagine we're looking down on it. But let me draw maybe right there, because I want to do a comparison between when the person on the carousel is right here and a moment later they're right here. And so I have a kind of a midway point straight up at the top in my picture. So I have something to discuss. So let's answer this in terms of the person right at the top. And of course they're heading in a direction that in a math class you would call tangent to the circle. So right here we would just be heading in a direction. Now I know if the carousel, let's say this was a little horse on the carousel, and for whatever reason it came unbolted. This is actually the direction it's moving, and so as soon as the bolts came loose, it would go straight off in that direction. Or if at the top, it would go straight off in this direction. And so what they're really after here in A is that you would be tangent to the circle. So maybe we'll just put tangent to circle. And that's what they want. That, hey, the direction is tangent to the circle. Now, of course, at the top, it looks like on the video here, it would be over here to the left. But I'm not going to put to the left because, down here at the bottom, clearly it would be to the right. And it would also depend which way the carousel's going around. So I want to kind of just leave it as a general answer here and go tangent to the circle. Now, B, C, and D are really one and the same, and actually the hard stuff. Because if you look at the definition of acceleration, it is the change in velocity with time taken. And, of course, if we're dealing with numbers and units, this is the formula. But we also like to put little arrowheads over there. And what this is really saying here is the direction of this and this are the same. See, these are equal. And so let me say it again. Not only is the number important, and not only are the units important, but also the direction is important. And so this little formula is saying, something to the effect of, let's say the change was 15, and let's say the time was 3, then you would get 15. So this formula is not just for the numbers, but it's also for the units. And so if this was 15 meters per second, and this was 3 seconds, then this answer over here would be 5 meters per second each second. And so I'll say it again, this formula is valid not just for the numbers, but it's also valid for the units, and probably haven't said enough of this, but it's also valid for the direction. And so this is saying whatever the direction of this one is the same as the direction of that one. Those two give you the same direction. So the little formula matches the numbers, matches the units, but also matches the direction. And the reason I say that is because B is looking for the change in velocity, and C is looking for the acceleration. And this little piece of formula is telling me that those are one and the same. And that's what I meant by saying these three are all the same. It's B and C, I've just hopefully shown you, would be the same. And then D is also fits here with Newton's second law. It says the net force is equal to ma. Now, let me again put a little arrowhead over the top. Because just like I said before, but it's probably worth repeating again, this little formula is saying not just about the numbers match, but also the units match, but also the direction matches. So, if I had a mass of 5 and an acceleration of 2, I would get a net force of 10. So yeah, the numbers match, but the units match. And so if the mass was 5 kilograms and the acceleration was 2 meters per second squared, then the net force would be 10, and I'd multiply these together and get a kilogram meter per second squared, which is what we call a Newton. So the numbers match in this formula. The units match in this formula. But let me say for this problem, the directions need to match for this. And so this is also saying that if you have, 5 kilograms and you have 2 meters per second, and this is, say, to the north, then over here you would get not only the numbers, the 10, and not only the units, Newton, but you would also get north. And so you can conclude that the force would be a number, a unit, and a direction. And that direction matches the direction on the other side, which is what D is all about. D says what is the direction of the net force. And I'm trying to show you that this little formula would then be saying that the direction of the acceleration and the direction of the net force would be the same. So that was my comment that really the parts B, C, and D, whatever direction they are, is the same thing. All right, so maybe that makes the problem a little bit easier because I just have to figure out one of these, and then I know all of them. All right, well, maybe I'll move on to a second page. Just for completeness, maybe I'll do all three of them. Maybe I will start with the simplest one. I think D is the simple one because what direction is the force? This was a part of the lecture. This was me tying a string on there. In fact, if you change this picture from a carousel going around and you put a little ball on here and you spin it, there's a tension in the string, and the string is pulling inward. And so right there, I would just say it is inward. It's the reason we called it a centripetal force. It's not outward. We don't call it a centrifugal force. We call it a centripetal force because it's inward. And that's probably the easiest one to see, and that's the one that I tried to do in the video lectures of me spinning a little ball. I think it was a racket ball on the end of a string and saying, okay, this is the inward force. And I even then said in the video lecture that, okay, once we know the direction of the force, we also know the direction of the acceleration. I took advantage of this equation by just saying they're one in the same. I suppose maybe a better way, and this would kind of tie in with B, is to actually draw a picture of it. And so let me look at B or C or B, whichever answer you want to look there. But if you kind of look at the direction that this one is headed, right here before it gets to the top, it's kind of headed off in this direction. Let me call that its initial velocity, because a moment later it goes over the top and then it's kind of angled down, and so let me draw this direction as the final velocity. And if you were to add the two, which I don't know why anybody would, but you would draw it like this. You would say, okay, this is the initial, and then this is the final. And this right here, from when you draw arrowhead to arrowhead, you would get the sum of the two. Now, I'll say it again, I don't know why anybody would want to do that, but I'm trying to help you with your vectors, because what I really want is the change in velocity, which is not them being added, but them being subtracted. And so how could I draw a picture of the vectors being subtracted? And I want to prove to you that this little arrowhead between the two tips of them would be their difference. Maybe the way to prove that is to say, well, this across here is question mark. And if you look at this picture, you'll see that from head to tail, this is initial, head to tail, this is the question mark. Those two added together would be final. So that picture is really saying that the initial plus the question mark is then equal to the final. Now, if I solve for a question mark, I would have final minus initial. And I guess I should have little arrowheads over this because they have direction. But that's my little proof to try to convince you that don't draw them head to tail, head to tail. That's the sum of the two. That's not what I want. You want the change in the velocity, so you want to subtract them. And the subtraction is when you draw tail end to tail end, and then you draw an arrowhead from tip to tip. And, of course, the one you finish on is the one that goes first. So this right here is my little proof of showing you this is the direction of delta V. Okay. And coming back to this picture, you'll see that, okay, this one, so this was going up and this was going down at an angle. Delta V is right towards the center of the circle. And you could do that anywhere along the circle, initial and final, and the delta V would be inward. And so hopefully that picture then fits all of this, and so we could say the change in velocity is inward. It is towards the center of the circle. And I'm hoping you see the delta V. And then again, saying that delta V is the same as the acceleration, so it's inward. And acceleration is the same as net force. Well, maybe I better call it quits on this video because, like I said, once you know one of them, and I think D is probably the easiest one because we did forces and tugging, and you can kind of feel and see that direction easier. But hopefully my little diagram also helped with the delta V. So anyways, these three are inward, and the A is the only different one. The velocity is tangential. Hopefully that helps.